Well, welcome back, everybody. Hope you guys had a good week. Here, let me let in a couple more people. Okay. Well, next week, next Friday, you have the next exam, which would be chapter 7, 8, and 9. The plan today is finish up chapter 9. We ended up in chapter 9. Then I forgot to go over some resources I gave you guys concerning the nomenclature aspect. So I'm going to go over those, and then whatever time's left over, then I'll jump into chapter 10. Okay. So any questions before we begin? All right. Well, my notes tell me we ended up on slide 7 of chapter 9. Okay. Now, what we've been talking about here, let me back it up a little bit just so we can refresh our memory. We're talking about acids and bases, okay? And then there's two definitions of acids. One is called the Arrhenius definition. And the Arrhenius definition is any compound that when put in an aqueous solution and dissociates, that's the important part, and dissociates and produces a proton, that is a hydrogen atom that has lost its electron, the H+, that's a proton, that is defined as an acid, okay? So hydrochloric acid, HCl, is an acid. It is a covalent compound, and previously I did mention that covalent compounds, when put in solution, do not dissociate, except for acids. So acids are the only covalent compounds that dissociate when placed into an aqueous solution, a water solution, and they produce a proton. That was the Arrhenius acid definition. The Arrhenius base was any compound that is dissolved in water again, and when it dissociates, produces the hydroxide polyatomic ion. Any OH negative that is produced, that is a base. And that definition worked fine for a while, but there's a lot of bases out there that have nothing to do with hydroxide. And therefore, Brownstein-Lowry introduced their definition of an acid and a base, and they stated that the acid, again, similar to Arrhenius definition, it produces or loses a proton. Both had the same definition, basically, right? Where they differ was how they handled the base. Brownstein-Lowry's definition of the base is a compound that actually accepts that proton. And that allowed a lot more multiple of compounds that can act as bases. And this example here would be ammonia. Recall when we did the Lewis dot structure for ammonia, we ended up with, refresh our memory here, we ended up with a lone pair of electrons on the central atom. Sitting right there, okay? And the proton, which is a plus sign, has that orbital, that 1s orbital, empty, okay? And so it will actually, the lone pair of the nitrogen can then bond in the empty orbital of the proton and forming the ammonium ion. See that? Okay, so here you have an example of a base that has nothing to do with hydroxide, but also is neutralizing that proton, interacting with it, okay? Now, with respect to what are called strong, and we're going to use the term strong and weak, both in the case of acids or bases. Now, a strong acid is simply this. It's an acid that when dissolved in water, completely dissociates approximately 100%, okay? And there are some examples of strong acids given here. The first one is HCl, very familiar acid. If not, it should be because it's in your stomach. Okay, hydrochloric acid, very strong acid. Okay, and it's strong because when in an aqueous environment, it completely dissociates, approximately 100%. Another strong acid is nitric acid. Okay, and then this is nitric acid. Notice the NO3. Does that look familiar? Nitrate. We'll get into the naming of these here when I'm done with this chapter, and we'll talk about the resources. The nitrate, when we put that hydrogen back on, we produce nitric acid. Then another strong acid, this one is called sulfuric acid. Okay, notice the SO4. Does that look familiar too? Polyatomic ion, sulfate. Putting those protons back on, you get sulfuric acid. All right, so those are three examples of very strong acids. Strong again because they dissociate 100%, roughly 100% in an aqueous solution, and producing quite a bit of proton. And so, for example, which is this kind of introduces a concept that we're going to be using quite a bit. If I have 100 units or 100 molecules of hydrochloric acid, and I dissolve it in H2O, I put that in the arrow to show it's going in solution, I will make 100 protons, and I will make 100 chloride ions, okay? And that's what we mean by dissociating completely. There wouldn't be any HCl left over that's still combined and together. Okay. Now, a lot of people have a trouble with this concept here, 100 HCl's to give me 100 protons and 100 chlorides. And the best way to think of this, maybe think of it as an analogy, is, oh, got a question, 1 second. Whoa, we didn't finish chapter, hold on. Okay. Oh, okay, good point. I just missed that. Somebody speak up. I'm sorry. Let me take a look. The reason I said that is because of my notes that I had here disappeared on my desk. So I went back online and I went to, let me check, to the videos I uploaded. And the video that I have, last SEC, is, oh, you are correct. I misread that. And up to slide 9 of chapter 8. Oh, thank you guys. I'm sorry. I was reading the wrong thing. Okay. It's chapter 8 of slide 9. Slide 9 of chapter 8. Okay, give me a second to regroup here. And we will. My apologies here. Okay, chapter 8, slide 9. That sound right? Everybody agree on that?
Yeah.
All right, thank you. Thank you very much. I just happened to look at that. Okay, let me. Give me 1 second here. Okay. All right. Okay. All right. Big time senior moment there. Okay. Everybody can see this? Oh, slide 9 of chapter 8. All right, we were talking about then polyatomic ions. Let's go back up there. So on your periodic table, on the far left, we have a table of what are called polyatomic ions, okay? The takeaway about this is that these things are units. We keep them together, and they each have their own specific name. Okay, so if we look at, say, hold on 1 second. If we look at, say, nitrate, which is this one right here, okay, it's a unit packet, if you will, that comes together with its own specific name. You might be tempted to call it nitrogen trioxide. Don't do that, okay? This is a ion, and it's made up of covalent compounds. A lot of them are made up of covalent compounds, but they have an overall charge. And if we ever need to have more than one, and then we utilize a parentheses. So if I needed to utilize more than one nitrate, I will put a parenthesis around it, and then I will put my subscript Q. Okay, so maybe calcium nitrate, okay? Will be that subscript Q. If we only need one, no parentheses is required. Okay, now, here we're gonna start writing ionic compounds, okay, writing formulas. Now, what we got to do is remember is going to write enough cations, have enough cations and anions, so when they combine, they equal 0. Okay. Now, to do this, we have to, you'll be given something, for example, like combine sodium and nitrogen and make them combine it to make an ionic compound. Well, before you can do that, the first thing you got to do is you got to convert them into ionic form. So as we know, sodium is in group 1, has 1 valence electron, so sodium will have a +1 charge, okay? Nitrogen is in group 5. So therefore, when nitrogen becomes an ion, it will pick up 3 electrons. Remember, the driving force is the octet. We also make note that nitrogen, with respect to the name, the non-metal with respect to his name changes its name. So it went from nitrogen, in this case, to nitride. Okay, the IDE. In fact, all of the non-metals, the oxygen becomes oxide, phosphorus becomes phosphide, all the halides, bromine, chlorine, iodine, fluorine becomes fluoride, bromine becomes bromide, etc. Nitrogen, as I stated, becomes nitride, and so forth. Okay. All right. Once we know what the ions are, now we put enough of each so they cancel their charge out. So we're going to have 3 positive sodium ions for every 1 nitrite. Okay. So that 3 that I put up here becomes the subscript for sodium. So the formula is Na3N, and its name is sodium nitrite. Remember the metal part, the metal doesn't change its name. Sodium remains sodium, whether it's an atom, an element, or an ion. Okay, so let's do a couple more. Okay, we're given sodium and sulfide. Well, same thing as I just stated. Convert everything first to ions. We just did sodium, so that we know that's sodium plus. Sulfur is in group 6, okay? So ionic sulfur becomes a -2 because it will pick up 2 electrons and become sulfide. Okay? So we're going to need 2 sodium for every 1 sulfide. Because remember, we want the number of cations plus the number of anions to equal 99% of the time equals 0. Occasionally, and I'll give some examples, it does not equal 0. It equals the charge of the species of what you're trying to calculate. For example, sulfate. Okay, you can use this general formula to calculate the oxidation number of sulfur in sulfate. Okay, we don't know what sulfur is. So we can say, well, it's sulfur plus, we got 4 oxygens, 4 of them, and we know that be it covalent, be it ionic, oxygens will always have a -2 charge, okay? And so there's a -2 in the oxygens, and that is equal to a -2 of the overall molecule. So we sulfur, we got sulfur -8 equals -2. Sulfur is equal to 8 -2 equals to +6. So in this state here, as a sulfur in the sulfate, as a sulfate ion, has a +6. Okay, and that's how we can use that equation here to figure out the charge. You're always going to know, think of it this way, it's an equation with 3 unknowns, cation, anion, and the charge of the molecule. You're always going to know 2 of those 3 unknowns. So it allows you to calculate, obviously, the third one, okay? So having said that, we got 2 sodium, 1 sulfur. Let me clean up my mess here so you can see a little better. So its formula is Na subscript 2S, okay? So, sodium sulfide. Okay, next one. Magnesium and oxygen. As I stated, converted first to ions. And the reason you do that again is because you want to make sure you add sufficient cations and sufficient anions so they cancel each other out. And that's why you got to put them in ionic form. And eventually, as you do more and more of these, you already know what they are, so you don't have to go through the step. I always advocate when you're learning something, you take a systematic approach of the steps that you're going to do to get to your answer. Until such time, you can bypass those steps and go right to the answer, and that just takes practice. Oxygen, as we talked about, always has a -2 charge. So I got the 2 ions, magnesium with a +2, oxygen with a -2. Its name now becomes oxide. Now I will go over the names, all the names after we're all done with the formulas. And so we put them together simply as a 1-to-1, 1 magnesium and 1 oxide, and that is the formula, magnesium oxide. Okay. Next one. We have potassium, like in sodium, is a group 1 element, so it always has a +1 charge. Phosphorus is a group 5, okay, just like nitrogen, and it will be a -3 charge when it becomes ionic because it picked up 3 electrons, excuse me, okay, and its name also now changes to phosphide. So we need 3 potassium ions to cancel out the -3 of the phosphide. So its formula now is K subscript 3 P for phosphide. Okay. Let's find this one. Let me clear this up. Now this one's a little more challenging, but that's okay. Okay, let's break it down. We got calcium. What do we know about calcium? It's a +2. Right? It's in group 2A. When it becomes ionic, it will lose those 2 valence electrons and become the calcium +2 ion. Nitrogen is a group 5A. and now it becomes a -3 charge of nitrite. And so the previous examples, we had a straightforward 1-to-1, 2-to-1 relationship, okay, or so no problem. However, here I got a +2 and a -3. And the question is, well, how do I put enough of each so they cancel each other out? Because the numbers don't jive here, don't match up. So my answer question to you then is this. If I have this fraction, 1/2 plus 1/3, what do I need to do to add those together? Obviously, I can't add them together as shown here. What is it that I need for 1/2 and 1/3, okay, to add them together?
The common denominator.
Common denominator, thank you very much. So what will be the common denominator for 1/2 and 1/3? What do you think?
6.
Exactly, 6. So I would multiply the 1/2 by 3, and that would give me 3/6, and then multiply the 1/3 by 2, and that gives me 2/6. So now I can add them, okay, end up with 5/6. Well, similar thing going on over here. I got to find a common denominator for these ions. So obviously, those two, the 2 and the 3, my common denominator is 6. Okay, and so I need to add enough -3s to give me 6. So obviously that's a 2. That gives me a total of -6 for the nitrites. Okay, for the calcium ion, I need to have 3 calcium ions because that gives me a total of +6. And guess what? Now I got +6, -6, that equals 0, okay? And so that 3 becomes the subscript for calcium, and that 2 in front of nitrogen becomes the subscript for nitrogen or nitrite. So the formula becomes C8 subscript 3, nitrogen subscript 2, okay? Also known as calcium nitrite. Okay. Aluminum, we know it's in group 3. It's a metal. It's going to lose 3 electrons. It will end up with a +3 charge. Chlorides are all in group 7, so they end up with a -1, right? So I need 3 chlorides for every aluminum +3 ion. And so that 3 is subscript for the chlorides, okay? And its formula becomes AlCl3. All right, zinc. Zinc, we know that it is A +2. It is part of the sweet 16. Did I mention those? Those 16 metals that 100% of the time they're charged, right? And then iodine, like chlorine is in group 7, so to become iodide, they gain 1 electron. So in this case, I only need 2 iodides for every zinc +2 ion. So its formula is ZnI subscript 2. Okay. Now here, up to this point, notice there were no Roman numerals because the sodium, the magnesium, the potassium, the calcium, and the aluminum and the zinc we just talked about have a fixed oxidation number, fixed charge. So therefore, when those they're all part of the 16, they don't require Roman numerals. That means that all the other metals have a variable oxidation state, and you have to either be told what it is or you can calculate it, okay? We can figure it out. So here you're being told because you're given the Roman numeral, and that means that the copper that you're utilizing is copper +2, okay? The oxygen, group 6, becomes -2 when it gains 2 electrons, becomes ionized, become an anion, and the name changes to oxide. Okay, so very straightforward here. We got, it's a 1-to-1 relationship, one copper ion +2 ion and 1 oxide ion to give you that formula. Okay, here lead is not part of the 16. So that tells you that Roman numeral means that you are working with Pb plus 4. Okay. Copper 4 plus 4. Oxide's the same, it's a -2. So you can see that I need 2 oxides to cancel out the +2 from lead 4. Okay. So its formula becomes PbO subscript 2. Now, with respect to naming, we got sodium sulfide. Okay. Second one is magnesium. Not to be confused with manganese. A lot of time Mg and Mn get confused, but Mg is magnesium oxide. Oxygen changes its name to oxide. Then we got potassium, Pb, going from phosphorus to phosphide. And then here we got again calcium and nitride. Okay, notice no Roman numerals here in naming them because these are the part of the fixed oxidation number charges. Then we have aluminum, chloride. Okay, and then Zn, which is zinc, and then iodide. Okay. Notice all the suffixes for the anion get changed to IDE, ND. Okay, the metals stay same, no Roman numerals. Here, because we're dealing with copper 2, we write it copper, and we have to include the Roman numeral, and then oxygen becomes oxide. Okay, that Roman numeral again belongs to the metal. You have to include that and use uppercase Roman numerals, not lowercase. Okay, now here we got lead, Roman numeral 4, oxide. Now think about canvas. Okay, if you write it lead and copper and then no space parentheses, that's fine. That's perfectly okay. If you write it with a space, that's also perfectly okay. However, we've been going through Canvas because I forget how many compounds we have. We got a lot of them. We've been changing them, correcting them. So if you ever write the correct name and it gets counted wrong, shoot me an email, okay? Because it's probably counting either space or lack of space is wrong. And I would definitely give you credit for that, you know, because to me, it doesn't make much difference if you put the parentheses, put a space before the parentheses or not. It's still, what's important is the parentheses and what that Roman number is. Okay, so keep an eye. So notice here again, stated, here we got the name, we got the formula. You know, I include both because questions are like that. Sometimes you're given the formula, you want the name. Sometimes you got the formula, the name, you want the formula, vice versa. Okay. All right. So the point again here, the takeaway is also when you put them together, you're given the elements, and then you got to convert those elements into what ions they're going to be, and then that tells you how many of each you're going to need. So you put enough cations, enough anions together so they cancel out to be 0. Okay. Now, with respect to the polyatomic ions, and that's that table. Where'd it go? Bear with me for a second. Okay. These are the polyatomic ions in the bottom left corner of the periodic table. Okay. So you're familiar with them. We're also going to be using the solubility rules table. That's the next chapter. And that's on the right corner. And then eventually we're going to use the activity series, but not right away. So there's a lot of information on the periodic table. I wrote in red here, the circled in red, the 16 metals that have a exact charge. Those are the sweet 16, as I call them. That means that all the other metals here have a variable charge, okay? And right here, variable charge. And you might say, well, wait a minute. What if I'm not given the variable charge? What if I'm given something like, I don't know, let's do a hypothetical, okay? So let's say I give you X and then Cl3, okay, as the formula. And you need to calculate what the charge is on X. X is a hypothetical element, okay? But what is it you do know? Well, you know that this thing is equal to 0, because it's neutral, okay? You also know we don't know what X is, whatever element it is. We don't know what the oxidation number is, but we do know that we have 3 chlorides. And what do you know about the chlorides? What is their charge when they become ionic? What is all the halides? What are their charges? The chloride, bromide, fluoride, iodide, what is their charge as anions?
-1.
You got it, -1. So we know that the chlorides have a -1. Okay, so I can rearrange this to say X minus 3 equals 0. What does that imply? X is equal to +3. So the oxidation number for X under these conditions is a +3. Okay. You can go the other direction. And this is knowing the charge of the anion, not knowing the charge of the cation. Let's do this scenario. Magnesium. Okay, magnesium, Y. Okay, hypothetical formula. Okay. Question is, what is the oxidation number of Y? What do you think Y would be? Anybody want to take a shot at that?
2 or -2?
-2, exactly, because what do we know about magnesium? Magnesium is a +2, okay? We don't know what Y is. It's a +1, so it's charged. So we got, Y will be equal to -2. It's charged because it has to be -2, correct? Because you want these to equal 0. Okay, so under these conditions, Y is a -2 charge. And magnesium, of course, is a +2 because we know it's in group 2 element, metal to be specific. So that's how you're, like I stated, you're always going to know of those 3 variables, 2 of them of the 3, and just using simple algebra. We're not doing very sophisticated algebra. Solve for the other, the number, the value for the other species. All right. So polyatomic ions, you're given the polyatomic ion, you're even given the charge, but we got to figure out the magnesium. So we know magnesium, obviously, we just talked about that, has a +2 charge because it's a group 2A metal, loses 2 electrons, and the hydroxide is given to you. Okay, so that means that because I got a +2 and a -1, I'm going to need at least 2. I'm going to need 2 hydroxides, and I just throw in my my parentheses because that's what I need to do when I need to show more than one of my polyatomic ions. And so I just take the charges off and I write the formula Mg parentheses OH and parentheses subscript 2. Okay. All right. We got the next one. Well, we got the phosphate, PO4 negative 3. Okay. And here, what do we know about potassium? It's in group 1. It's going to have a +1 charge. All right. So we're going to need 3 potassium ions to balance the -3 of the phosphate. Okay. So that 3 becomes a subscript, and hence its formula is K subscript 3 PO4. Now here we only needed 1 polyatomic ion, so you don't need to put the parentheses. It's just 1. Okay. K2 PO4. All right. Next one. We got the question here. Ooh, not to worry, Trevor. Okay. So here we break it down into the ions. Again, silver, 1 to the 16, always has a +1. And then the sulfate has a -2. So that tells you I need 2 silver ions to balance out the sulfate polyatomic ion. And so its formula now becomes Ag subscript 2 SO4. And like in example number 2, we only use 1 sulfate SO4, so we don't need a parenthesis. Okay, calcium. We got calcium, which is a +2. And we got the nitrates, which are -1. So guess what? We need 2 of those guys. All right. So I just take off the charges, put them together, and now the formula is Ca parentheses NO3 and parentheses subscript 2 nitrate. We'll get to the names here in a bit. Okay. All right. We're, as a previous example in the previous slide, copper Roman numeral 2 tells us we're working with copper +2. And then we got the CO3 -2, which is the carbonate. And since we got a +2 and -2, we can simply put them together as a 1-to-1, and we end up with the following formula: copper CO3. What if you were given copper Roman numeral 1? What do you think the formula would be? And the carbonate. Okay, what would be a formula for copper 1? Copper 1 tells me I'm using a +1. Okay. And the carbonate is still -2, hasn't changed. So that means I need 2 copper 1 ions. So that becomes copper 2 CO3. See, these are 2 completely different compounds, completely different. Different properties, different everything. Their parent name is the same, copper carbonate. But the difference is the Roman numeral to tell us what charge is that copper exists. Okay. And the old naming, they still use it to a certain extent, is cupric and cuprous. And that was quite ambiguous because the ick and the us got to be confusing. So to stop all that, they adopted the Roman numeral, and there's no question now, no ambiguity involved here. Okay, so remember to use the parentheses when more or one of the polyatomic ions are needed. And so here, with respect to the name, we have magnesium, okay, hydroxide, You will find, if you Google the term, you will find oxygen hydride or oxygen hydrogen or some name. That don't do that, okay? OH is hydroxide, okay? And you also will find, if you Google some of these compounds, you'll find ic, cupric, and cupres. Don't do that either. Okay, use the Roman numeral nomenclature. This one is simply potassium phosphate. Notice if you're looking at your polyatomic ion table, that is the name of that polyatomic ion, phosphate. It's not phosphorus tetraoxide. That's not the name of that. Next one is simply silver sulfate. Okay. It is not sulfur tetraoxide. Sulfate. Then here we got calcium nitrate. Again, it is not nitrogen trioxide. Okay, it's nitrate. It is a polyatomic ion name. And then the last one, we have to include the Roman numeral. So it's copper Roman numeral 2 carbonate. Okay. And again, I give you the name so you can go to the formula, vice versa, back and forth. All right, so this is basically summarizing everything we just did, naming the ionic compounds, okay? Write the ionic formulas, and then depending on the charge, whether the metal is fixed or no variable, determine that. We use Roman numerals only for those variable charge metals. Everything else, no Roman numerals, okay? The chlorine, we talked at length about this. All of the elements, the anions get their name changed from INE to IDE. So chlorine becomes chloride in this form, okay? So that's sodium chloride for Na, okay? Here we have KBr, all right? So we have potassium for K, and we say bromine for Br, but it's bonded, it's ionic compound with potassium, so bromine gets its name changed to bromide, okay? So potassium bromide. Here, the same thing, magnesium, oxygen, when it becomes anionic, now is oxide. So that is magnesium oxide. And then here we got calcium. You might think, oh, that's diatomic fluorine, but it's not. Okay, don't let that too confuse you, because right before that F is calcium. That tells you you're dealing with an ionic compound. You're not dealing with diatomic fluorine. So that's calcium chloride, just like the chloride, just like the iodide. Okay. Here we got lithium. And then the sulfur, when it becomes ionic, is sulfide. Notice the trend on the anions, IDE, 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 all the way down. Okay. And then we got silver. Chlorine becomes chloride, just like the fluoride and just like the bromide. Okay. Now, the important aspect about ionic compounds is there are no prefixes. Okay, what do I mean by prefixes? And so, for example, lithium sulfide is the name. It is not dilithium. Not dilithium. It is not, it's calcium fluoride. It is not calcium difluoride. Okay, so on and so forth. The only dilithium I'm aware of is dilithium crystals in Star Trek. I don't know. But we don't use it. So ionic compounds, important. Ionic compounds, metal, non-metal combinations, no prefixes. Unlike covalent, where we use prefixes, okay? Like carbon dioxide, carbon monoxide, et cetera, et cetera. Also at this point, with all the ones we've been working with, all the ones in naming we did a previous page, you can start mixing and matching here, okay? Because you can take the magnesium and hook it up with the phosphate, sulfate, nitrate, take the potassium, go with the hydroxide, go with the sulfate, go with the nitrate, go with the carbonate. And the same is true with calcium, calcium hydroxide, calcium phosphate, calcium sulfate, calcium carbonate. Okay, so you can do a lot of mix and matching and start building up your database of chemical compounds. Okay, same as here. We did it. You can do potassium oxide, potassium fluoride, potassium sulfide, potassium chloride, et cetera, et cetera. Okay, so you probably got, I don't know, 400 or 500 compounds that you can mix and match, and that's just including the metals we talked about, because every other metal up there you can do the same to that. So you have quite a database of compounds that you can create. Okay, naming the polyatomic ions, as I mentioned, we don't change the name. So you might say, well, wait a minute. How do I recognize it is a polyatomic ion? Well, let me give you a little something to work with that might help. If you see it, then and how you identify it, and you're good with that, okay, don't let me change your method, whatever works for you. But if you don't see it, I don't know, you might try this. All right, so here I got potassium, 3 of them. And then I see phosphorus, okay? And so I might be thinking, okay, phosphorus, maybe we're phosphide, right? But right immediately following phosphorus, we have oxygen immediately. And that is true for the sulfate ion. We got sulfur, but right immediately bonded to it is the oxygen, okay? And look at that, nitrogen, same thing. Okay, we got nitrogen, then right immediately bonded right next to it, you see oxygen. That is a good indication you're dealing with, at least in Chem 130, you're dealing with a polyatomic ion, PO4. So that can direct you to the polyatomic ion table to figure out what its name is until you become familiar with it, okay? And more comfortable with it. So unlike this one, if I were to have written, and let's make sure I got a real one here. Okay. Let's say I would have done this, written this, KPP. It's a legitimate compound. That's phosphide, potassium phosphide. Okay. I saw phosphorus all there. There's no oxygen next to it. And so that tells me I'm dealing with phosphide. Okay. And this one's potassium phosphide. I look over here, this is the potassium phosphate, ATE. The IDE always should tell you you're dealing with the single element, just the sulfide, just the sulfur, oxide, just the oxygen, okay? Fluoride, just fluoride. So, and then we're going to have ITE, phosphite. We're going to have in our additional resources how that works, and I'll show you how that works. Okay, so here this up, and so we have a polyatomic ion. So its name, I go to the table, look it up, PO4, that's the phosphide, potassium phosphide. All right, the parentheses, the fact that there's a parenthesis should direct you to the polyatomic ion automatically, because the parentheses is used when we need to add or utilize more than one polyatomic ion, okay? Notice there's no parentheses in the first one, so I relied on looking at the phosphorus and then seeing that there is an oxygen bonded to it right immediately. And that's how I determine it's a polyatomic ion. But I see a parentheses, don't have to go any further. I got a polyatomic ion. I go look it up. OH is a hydroxide, its name. And Ca is simply calcium. So we have calcium hydroxide. Okay. Again, SO4, just like the phosphate, we got sulfur and we got oxygen. Polyatomic ion, go to the table. There's 4 oxygens. This is the sulfate. If it had 3, it would be the ITE, the sulfite. In fact, the difference between the ATE and the ITE is 1 oxygen difference. The phosphite would have PO3. Okay, the sulfite will have SO3. But this is SO4, sulfate. All right, let me clear this up. And then sulfite. Variable charge metal ionic compounds. We talked at this. You got the metal name plus the Roman numeral. Then, of course, the non-metal part with the IDE. And so here the question is, well, how can I figure it out? Well, you got to remember the total cations plus the total anions equals 0. So for the variable charge elements, you have to determine what the charge is on the metal. And we know that the chlorides are all -1 and that there are 2 of them. So that gives you a total -2 charge. And the overall molecule charge is 0. That tells you that copper here is a copper +2. Okay? And we work that through. And so put into a simple formula. I got Cu, which I don't know what its charge is, but I do know that there's 2 chlorides and each one is a -1. And that whole thing equals 0. That molecule equals 0. Okay? It's a neutral species. So that means that Cu -2 equals 0. And so obviously Cu is equal to a +2. If it's a +2, then it's got to be copper Roman numeral 2 is the name for that copper. Chloride. Copper Roman numeral 2 chloride. Okay. Well, here we go with oxide, lead oxide. We know that the parent name is lead oxide. Okay. And it would be incorrect just to say lead oxide because lead is not part of the sweet 16. The 16 are a fixed charge. Lead is not part of it. So we have to calculate and determine what it is. And so we know that we got Pb, and we know that there are 2 oxygens and each one has a -2 charge. Okay, so Pb -4 equals 0. Obviously, Pb has to equal +4. Okay, so this is a +4, which means that now the name is lead, parentheses, IV. IV. All right, lead Roman numeral 4 oxide. Okay, nickel. Break it down. We got nickel plus, we have 3 bromides, and each one's a -1, and that equals 0. So we have nickel -3 equals 0. Nickel nickel has to equal +3, and so therefore it's Ni parentheses Roman numeral 3. I didn't spell it out, but I just did the symbol, but you can spell it out. NiCl. NiCkel, nickel, Roman numeral 3. Okay. Manganese, not to be confused with magnesium, Mg. Okay. So if you look at that, I'm not going to work it through, but what do you think is the the name for this species, MnSO4. What do you guys think?
Manganese sulfate. That's all I have.
Okay, well, you got the parent name correct. Did you give it a Roman numeral?
4.
Oh, 2.
2, Roman numeral 2, exactly. Because remember, you got to keep, when you look at these formulas, look at the metals first and ask yourself, okay, are these part of that 16? The ones that I circled here in red, because those are the ones that we have a constant oxidation number charge all the time, 100%. That's what they are, which implies that everything else, all the other metals here vary. And it all depends on what their partner is and what their anions they're bonded. Okay. And so manganese is not part of it. Manganese is not part of the 16. It requires a Roman numeral, and you have to calculate it based on what the anion is. And like you said, the sulfate is a -2, so that means this is a Roman numeral 2. Manganese, Roman numeral 2, sulfate. Okay. All right, I think I got one more, maybe, yeah. Okay, here we got copper NO3. Anybody want to take a shot at that one? How would I name that one? Okay, what is the name of NO3?
So NO3 on the most common polyatomic ions list is nitrate, and there's a -1 above the 3, so it'd be copper 1 nitrate.
You got it, exactly. Okay, copper 1 nitrate. Okay. The NO3 -1 would be nitrite. So you gotta be careful with these polyatomic ions. We're gonna run through some examples. There could be more than one polyatomic ion. Of the same sense. Okay, now we got CON. Now here's a case where I look at nitrogen, I might be thinking nitrate, nitrite, but guess what? There's no oxygen bonded right next to the nitrogen, like there was in number 4. So that means it's just nitrogen all by itself, which its oxidation state is a -3 nitride, which implies that the cobalt has to be a +3. So cobalt minus a -3, okay, because that's the nitride. The nitride has a -3 and there's 1. And so cobalt has to be a +3. And so therefore it is cobalt Roman numeral 3 nitride. Okay. Note the difference here, the 8 and the ide of the nitrogen. The 8 is nitrogen bonded with oxygen. The ide is just nitrogen all by itself. Very similar to sulfate, where sulfide would be just sulfur all by itself. Okay. Oh, one more. All right, a little more challenging, but yeah, let's break it down. What do I notice here? Here are a couple of things here. Obviously, I got a parentheses, so that tells you I got polyatomic ions. So then I look and I look up the CO3, which is carbonate. And then also from the table, the CO3 tells me I have a -2 charge on that, right? All right. And I have 3 of them. 3 of them. So that means I got a total of a -6. I got 3 of the carbonates, and that equals to a total of -6 charge. All right. Now, the other thing I see, I got 2 irons. So I can set up my equation. 2Fe, because I got 2 irons, -6, because I got 3 carbonates, each have a -2 charge, and that is equal to 0. Okay, and so I rearrange the equation. I got 2Fe iron is equal to +6. Okay, now I divide by 2. Then I want to get rid of that 2 and isolate iron. And so iron in this state is a +3 state. Okay, and so the iron, the name of this compound would be iron +3 carbonate. Okay. Now notice something interesting is you can go through that exercise I just did, breaking it down. Okay. But I did mention a while back when you have dissimilar charges that I said, notice that the subscript of the anion is the charge of the cation. And I said the subscript of the cation is the charge of the anion. Didn't we just calculate a +3 for the iron? And isn't that the subscript of the anion? Yes, it is. And do we know that the carbonates are a -2, which happens to be the subscript of the cation? So you can use that. So you can look at a glance and know right away that's iron 3 carbonate, because that's the subscript on my anion. Okay. Or if you don't see that, then work it through the way we just did over here to show that, yes, it's a +3. And there's 2 irons, so each one is a +3. Okay. Let's talk through these. Okay, so here, let's talk through because we got SR, which is strontium, okay, and then we got the polyatomic ion hydroxide. All right, so we got to put them together, but first we got to find where SR is, and SR is a metal, and it is a group 2 metal. So that means that it will have a +2 charge. It becomes ionic, which means that since the hydroxides are each -1, I need a parentheses, and guess what? I need 2 of them. So my formula is SR parentheses OH subscript 2. And the name is strontium hydroxide. Okay, here we have AU and Cl. Well, AU is gold, not to be confused with AG, which is silver. So we got the name here, okay? And then Cls, we know they're chlorides, okay? So we got that name down. Question is, still gold, I got silver in the head. Gold is not part of the 16, so I need a Roman numeral. So I need to figure it out. So what does this mean? Well, each chloride's a -1. So that implies that I got a total of -3 for the chlorides, which tells you that gold has to be a +3. So therefore I use Roman numeral 3. Okay. All right, zinc and oxygen. Well, break them, put them into ionic form. We know that zinc is a +2 and oxygen becomes oxide with a -2. So we can simply put them together as a 1-to-1. They cancel each other out. So the formula is ZnO, and its name would be zinc oxide. All right. PO4, -3, it's one of the polyatomic ions. Barium is a group 2 element. So we know in ionic form, this would be a +2. And so now we have a dissimilar charges, but that's okay. We need to find a common number. right? So we need here a common number 6. So we need 3 bariums to give me a total of +6. And we need 2 phosphates to give me a total of a -6, okay? So that 2 and that 3 becomes the subscript. So it becomes Ba3, and since we need 2 phosphates, we need a parentheses. And so parentheses PO4 and parentheses subscript 2. And the name is simply barium phosphate. Okay. Lithium. Lithium is in group 1 metal. That tells you that it's ionic form, it's going to be a +1 charge. Then we got SO4. At first glance, you might want to think sulfate. But looking at your table, you see, looking at this, you see it's a 3. And then looking at your table for an SO3, you see that there is that is called sulfite. Okay. And so we got the parent name here, sulfite. And then we got lithium and simply lithium sulfite. We need 2 of them, 2 lithium ions to cancel out the -2 of the sulfite. We got sulfur, number 6, all by itself, which means it is sulfide. Its ionic charge is plus a -2, right? It's in group 6, so it's got a -2. The aluminum is in group 3, and they will end up with a +3 charge when it becomes ionic. So again, we have a dissimilar charges. No big deal. We'll find a common number. We need 2 aluminums and 3 sulfides. Common number 6. Okay, so we need a total of 6 pluses and 6 negatives. And so our formula becomes Al subscript 2 sulfide subscript 3. This one here, the last one, they're asking you just for the name. Well, we have to figure out what copper is being utilized here. And we got a polyatomic ion. How do I know that? Because I got a parentheses. That's my hint, first hint, got a parentheses. So I go to the table, look for NO3, and yes, it's called nitrate. Furthermore, each one has got a -1 charge, but there's 2 of them. So I got a total of -2. That implies that copper has to be a +2. Okay, because I got a -2 for the nitrate. You got 2 nitrates. Therefore, the name of the species is copper, Roman numeral 2, nitrate. Okay, so just by breaking it down into the ions, and then for the ones that have a fixed oxidation or charge, straightforward, just adding up of each. For those that vary, you would know the anion, the metals, that is, you would know the anion charge. You can calculate what that variable charge would be. Okay. Okay, here's examples that they're asking you to give the formula. I'm just going to go ahead and give it to you here. We got sodium, which we know is Na plus, and we got nitrite, which we know from the table. Notice the ITE. That is the NO2 -1. Okay, it's not the nitrate, it's the nitrite, which is -1 less, not minus, less 1 oxygen than the 8. Okay, so we can simply put them together in the 1-to-1 ratio because it's +1 and -1. Okay. Oxides, we know it's a -2. And here you're being told you're working with nickel +3. So again, we got dissimilar charges. We find a common number, which is 6. So we need 2 nickels and 3 oxides. Okay, so our formula becomes nickel, Ni subscript 2, O subscript 3. Magnesium is a +2. It's a group 2 metal. The iodides are -1, so we need 2 iodides. Okay, so we can simply make that Mgi subscript 2. And then aluminum always has a +3. And then cyanide, that is a polyatomic ion, which you can find on the table again. And it's Cn-. And so that means we need 3 cyanides, which tells us we're going to need a parentheses. And hence the formula is Al, parentheses, capital C, capital N, and parentheses 3. Okay. Very fine. Let's take a very short break. I tell you what, let's come back at say 2:30. Let's come back at 2:30. Okay. All right. Then we'll talk about molecular and covalent compounds. Okay, I'm back. All right, so up to this point, we've been working with ionic compounds, okay? Also, too, I've been using the term charge. The cation has a charge of +1, +2, anion has charge of whatever charge. But I'm going to start using the term oxidation number, okay? Because in ionic compounds, yes, recall it's a full-fledged charge, +1, -1, whatever, it's a full-fledged charge. Covalent compounds, there's not a partial charge, okay? And so we can't really talk about a charge in a covalent compound, so we use the term oxidation number to encompass both the, quote, charge of ionic and whatever partial charge of covalent. Okay, so when I say the term oxidation number, it's still the oxidation number of the sodium ion is a +1. The oxidation of an oxide ion or an oxygen is an ionic form or bonded covalently. Let me restate that. The oxidation number of an oxygen that is either bonded covalently or ionically is still -2. Okay, does that make sense? All right. Also, with respect to the anions, when we dealt with the ionic compounds, I stated oxygen, for example, its name becomes oxide, the chloride becomes chloride. Well, the same is true for covalent compounds. That naming still remains the same. In covalent compounds, remember, we're going to have a central atom, and then whatever is bonded to the central atom. And that other atom will have its name changed to the IDE suffix, okay? Now, as you know, covalent molecular compounds are compounds made up of nonmetals. Now, we will use prefixes, okay? So the prefix for 1 is mono, 2 is di, 3 is tri, tetra for 4, penta for 5, hexa for 6, and hepta for 7, and octa for 8. Nana, N-O-N-A, is 9, and deca is 10. Okay. So how we name these things? Well, similar as we did with ionic, but the difference being we may have to use prefixes. So we have the nonmetal name, okay, generally the central atom, and if we have only one, it's just whatever the name it is. We don't use the prefix unless there's more than one. So we could say di-carbon, di something, okay? Then we add the prefix for the second nonmetal, and we change its name to the IDE, just like we did with ionic compounds. So we have a prefix, or you have, for example, CO2, carbon dioxide, because that's 2 oxygens. All right. If the first metal is by itself, we just leave it alone. We just give it its name. Okay, so classic example is C, 2 oxygens, okay, aka carbon dioxide. Okay, only one carbon, so we just leave it as carbon. And then di because there are two oxygens. When you have one oxygen, now you use the prefix mono. Okay, so we have carbon monoxide, totally different, as you well know, than carbon dioxide. Okay. So here, my suggestion, until you become comfortable, is to first write the parent name, like, you know, the base name, I should say. So what we got here is phosphorus and oxygen, otherwise known as oxide. So we simply write phosphorus, and then the oxygen as in ionic compounds, the name is oxide, okay? So that's the base name. Then we go back and check the prefixes. There's a 2 for phosphorus, so that becomes di, there's the prefix, and there's 5 for oxygen, so that becomes, the prefix becomes penta. Now, the problem is this, is that, okay, we have penta that ends in A, and we're going to connect it to an O. So we got 2 vowels coming together. From an English perspective, you have to drop the A, so it's actually pentoxide, okay? Now, if you forget to drop the A, I'm not going to make a big deal out of it. That's fine. Pentoxide with or without the A will be fine. You won't be counted wrong. If you are counted wrong, let me know in Canvas, and I will give you your credit. So that is called diphosphorus pentoxide. All right, similar scenario. Notice the phosphorus is the first element, the central atom, so we keep the name phosphorus. If it was the second element, then we will change its name to phosphide, but it's not. It's the first element, so we maintain phosphorus. And then we got fluorine, which is, we change its name to chloride, just like we do with ionic compounds. And we add the prefix because there's 3 fluorides. And hence this becomes phosphorus trifluoride, okay? Don't need to add the mono because it's just, that's it. We got just the 1 atom up front. All right, now we have the parent name would be iodine. Well, you got iodine. Okay, now notice it's iodine because it is the central atom, or you'll always be, the central atom will be written first. Okay, it is not iodide. If it's secondary element, then yes, it would be iodide. Then we got fluorine, but it's a secondary, so it becomes fluoride. Okay, so that is our base name. Okay, then we come back and check for the quantity. There's only 1 iodine, so we leave it as iodine. And then we got hepta for 7 because there's 7 iodides. So we insert that and name it iodine heptachloride. Then notice we didn't drop the A there because the F is not a vowel, it's a consonant, right? All right, then we have, oh, so here, the takeaway here is this. 1, we use prefixes for the elements for covalent compounds only, okay? Prefixes. If it is the central atom, which is normally the first one, we don't, if it's like I said earlier, iodide is here, number 4, it's a central atom. So its name remains as iodine. And if it was something else, it was a secondary atom, then it would be called iodide. Okay, let me give you an example of what I was trying to explain. What if it was sulfur and 3 iodide? So this would be sulfur tri iodide. Okay, now it's iodide because it is bonded to the central atom. Here is iodine because it is the central atom. Note the difference, okay? All right. So given the formula, write the name and vice versa. So we have Br308. Okay, so they're asking for the name. And again, my suggestion is to write the base name, which we got bromine. Okay. So we write bromine. And then we got oxygen again, which is oxide. Okay. Now we look at the prefixes. So that's tri for 3 and octa for 8. And we got 2 vowels coming together. So we drop the A and becomes octoxide. But as I stated, if you leave the A in, okay, no big deal. I won't count it off. Okay, we got phosphorus and sulfur, parent name, phosphorus sulfide. Okay, phosphorus sulfide. And then we got the prefixes 4 for tetra, 7 for hepta. So we have tetraphosphorus heptasulfide. Okay, you know, if this was SO3, this sulfur is sulfur. Okay, because it's the central atom. Here in this case, it's not the central atom, hence it becomes sulfide. This would be sulfur trioxide. Okay. All right, one more. Here we go. Sulfur, and then 3 oxides, trioxides. So note the difference there, how sulfide is used and how sulfur is used, depending if it is a central atom. Now you're given the formula, the name, you want to know the formula, right? So we got iodine, which you know is I, and then we got fluoride, which you know is F. Now you come back and do the prefixes. There's hexa, means 6, so that would be the formula, IF6. Okay, and here we have parent base name chlorine oxide, so that would be Cl and O. Prefix di gives us 2 penta, meaning 5 oxides. So there's the formula. Okay. Okay, and we got here phosphorus and iodine. So we got phosphorus iodine. Okay. And then go back and do the prefixes. So it's diphosphorus tetraiodine, dropping the A, but you can leave it there. Okay. So reminders, prefixes only for covalent compounds. Okay. Roman numerals only for those metals that have a variable charge or oxidation number. Okay. The metal compounds. And polyatomic ions don't change their name. They each have their own individual name. Their name stays. Okay. And so you might want to try these. I'll go ahead and give them to you, the answer, and then try these at home. You got barium, chloride, nitrogen dioxide. See if you come up with the same answers that I get. Try do it without, well, you got the answers here, but see how the answers were derived. And then check yourself, make sure you understand how that happened. If not, next Friday, feel free to bring them into class and we can go over it, or shoot me an email and we'll talk about it, okay? There's some more. And there is a worksheet. So the more practice, the better for you. So don't forget to do that to help you out. All right, other than that, you are done with chapter 9. Do you have any questions? Any questions? Okay, I was going to do some more nomenclature, but since a lot of it's self-explanatory, but I'm going to go on and jump into chapter 9. Okay, and then given time, we'll come back and do that other additional resources with respect to nomenclature, because that we can do anytime, because that's really helpful for the nomenclature exam, which, by the way, remember, don't forget, you have an unlimited number of attempts to knock it out. So you got to get at least an 80% the passing grade, and you can continue repeating the exam until you're happy with the grade that you have. If you're happy at the 80, then you're good. A lot of people have asked me, does it really affect me? And the answer, well, it could. It depends if you're on the border. If you're on the border, either border, a border to move up or a border to drop down. Yes, that 10% could affect that, okay? It can help your grade, or it can actually drop you back down. And that's why I added zeros to them now early in the semester. So you can truly see your true grade without it, okay? Because Canvas doesn't, the grade that you have now that you see is just for things that have been graded. It doesn't take into account future assignments, okay? All right, any questions? And that, let me jump right in here, okay? This chapter deals with acids and bases. Okay. Now, let me say something here about hydrogen, because we're dealing with proton. Hydrogen is very unique, okay? Hydrogen, its Lewis dot structure is 1 dot. It's the first element, right? Now, its electron configuration is 1s1. It has 1 electron in the s orbit, the very first orbit. Now, remember that every orbit, be it s, p, d, or f, can handle 2 electrons. So hydrogen by itself, the atom hydrogen, can actually gain an electron. And when it does that, because it has room in the s orbit, okay? And it picks up an electron, and now it has an overall -1 charge because it has 1 proton, 2 electrons now, right? 1 proton and 2 electrons, so the net is -1 charge, okay? As the atom has got 1 proton plus 1 electron, okay, net is 0. Okay, so this guy, when it gains an electron, it's called hydride. Very crucial compound in chemistry, especially organic chemistry. But the other aspect is this, that 1 valence electron can also be lost. That's why it's in group 1. A lot of times hydrogen in some periodic tables are actually put in group 7, okay? Because they can pick up 1 electron like all the halogens. And guess what? Chlorine becomes chloride. Look what happened to hydrogen. Became hydride, name-wise, okay? But it can lose that 1 electron, so now it's got a +1 charge because that 1s orbital is now empty, no electrons. So it simply has 1 proton. So its net now is a +1 charge. This is what we call a proton. This is the acid that part of a chemical that is called an acid. Is any chemical that when dissolved in aqueous solutions produces a proton, okay? Now, I also mentioned that an example of an acid would be hydrochloric acid, okay? And this is a covalent compound. Acids are covalent compounds. And those are the only compounds that when they are placed in water, they completely dissociate, they break apart into those ions. So hydrochloric acid, when that is placed in water, can break up into the ions and be solvated by water, totally broken apart, okay? And it becomes ionic, and it produces the H plus. That is what we call, like I stated, a proton, and that is what is the acid part of a chemical, okay? So some properties about an acid, which you're familiar with, okay? They tend to taste sour. Vinegar, pretty sour, right? Lemon, grapefruit, those are acids and very acidic. And also very corrosive. They will break down metals, some metals, not all, but some. They can be very corrosive. And there is a test for them, and it's a real simple test. We have what's called blue litmus paper, and it's a pH test. It's just if you dip blue litmus paper into a solution, it turns red. That just tells you it's an acid. It doesn't tell you how strong it is. It just says it's an acid. Okay. All right. With respect to bases, now we have two types of definitions for bases, and the majority of definitions deal with this polyatomic ion that you should become well familiar with. Okay. And that is the hydroxide ion. And so that any compound that when you place it in water dissociates and produces that polyatomic ion is considered a base. Okay. If in the solid form, I wouldn't taste it, but they do taste bitter and they're kind of chalky. And if you ever get some in your finger, they feel slimy. Okay. If you ever had liquid plumber, for example, in your finger, use it at home to unclog your drains, it's slimy. And you might think it's a chemical. It really isn't the chemical. A lot of it is your tissue being broken down. Strong bases tend to help and will dissolve tissue, soft tissue. Now, as we have blue litmus paper, we got red litmus paper. So if we take red litmus paper, put it in a solution, it turns blue, again, that indicates you have base. Okay, we're going to talk about the pH. And in the pH, we have a range from 0 to 14. 7 is neutral. Anything less than 7 is acidic. Anything greater than 7 is basic. Okay, we'll have more to say about that in a bit. Now, here's the thing about this up here. The definitions. There's two definitions. The first definition is called Arrhenius acid or base. That is any compound that when dissolved in water dissociates, it produces the proton H plus, okay? It's an aqueous solution. When we talk about acids and bases, we're talking about aqueous solutions, water solutions. Hence, we use the AQ to designate it as an aqueous solution. So you can see H hydrochloric acid dissociating here. And sodium hydroxide is a good example of a base, okay? Any hydroxide. Notice that Arrhenius bases tend to be ionic compounds. Sodium hydroxide is an ionic compound. Arrhenius acids tend to be covalent compounds. HCl, we have some more, we're going to talk about covalent compounds, all right? Now, sodium hydroxide, when it's placed in water, will dissociate. And it will break it into their own respective ions, sodium ion and the hydroxide ion. Okay. Now, a thing about the reaction of a proton and a hydroxide, when they come together, they form water. Okay. They neutralize each other. Okay. So hydroxide reacts with a proton and get neutralized, and we end up with water. Now, the way that works, if you were to think about it, is if we were to do the Lewis dot structure for the hydroxide ion, you will find it's a negative charge, and it's got 3 lone pairs around the oxygen. The hydrogen is empty. Okay, that orbital is empty. And so this orbital here can combine that empty orbit of the proton and that filled orbit of the lone pair and the hydroxide combine to form water. Okay. And that is one of your first types of reactions that we're going to introduce, and that's a neutralization reaction. More on that acid-base reaction here in a bit. Now, that's what we'll talk about, a neutralization. When an acid plus a base react, you form water is the component because you neutralize the acid and the base, and you form a salt. Now, you may be familiar, when you think of salt, you might be thinking about, in this case, sodium chloride. But a salt is any ionic compound, okay? All ionic compounds are salts, and it's a combination of a metal and non-metal. Now, if we take hydrochloric acid, put it in water, it dissociates to form the proton. If we take sodium hydroxide, like I showed in the previous slide, we put in water, it will dissociate to produce hydroxide. And as I stated earlier, the proton plus the hydroxide react together to form water, okay? And then what's left over are the corresponding anion and cation. And so the cation of the base combines with the anion of the acid to form the salt. So in this case, we form sodium chloride. But it could have been potassium chloride, any other hydroxide that could have been utilized, okay? So this is your first introduction to reactions. And this one happens to be neutralization. There's 6 types. This is the first type. Okay, so here's something to think about. Now, make your own decision. We have a base here reacting with acid that gets neutralized to form water. Now, a student once asked me about this alkaline water that's out in the market and if I knew of any benefits. And, I said, no, I really don't as far as any health benefits, but I can tell you the basic chemistry. If you take a base and your stomach is nothing but hydrochloric acid, what do you think is going to happen to the alkaline water that you drink? It's going to get neutralized into water. And so what other salts are in there that may be beneficial? I don't know, but I can tell you this, that the pH of your alkaline water is neutralized the moment it interacts with the hydrochloric acid in your stomach. Think about it. When you have an acid, what do you take? You take Tums. Tums is a base. You want to reduce the acid reflux you got going on, and so it gets neutralized. So you're neutralizing the acid in your stomach. Or milk or magnesia. That's another one. It's another base. Okay. And now, if you don't have any milk or magnesia in Tums, maybe drink some alkaline water. All right. So the Arrhenius definition encompassed a lot of hydroxide. It was based on the hydroxide base. However, there are examples of bases that have nothing to do with hydroxide. And so Brownson and Lowry had to come up with an additional definition of an acid and a base and to encompass a lot more reactions. So basically both Arrhenius and Brownson are basically the same definition for an acid. Brownson and Lowry says it loses an acid. Arrhenius says, it loses a proton. Arrhenius says it produces proton. Produces protons made, okay? In my eyes, they're both the same definition. Where they differ is the base. Whereas the Arrhenius base deals with hydroxide, Brownson Lowry deals with a chemical that will set that proton. Okay, if you recall, we did Lewis dot structure for ammonia. This is ammonia we're working with right here. And if you recall, we had a lone pair of electrons on that central atom. Okay, earlier I demonstrated that with the hydroxide and the proton, that proton has an empty 1s orbit, right? Empty 1s orbit that it can then hook up and bond with that lone pair and stabilize that proton and neutralize that proton. Okay, and so now you created the ammonium salt. Now, this is another way to neutralize the scent of ammonia. We've all smelled ammonia, right? And so you can treat that with a little bit of maybe acetic acid, vinegar, or some hydrochloric acid or muriatic acid, which is hydrochloric acid. And you can neutralize that ammonia, forming a salt. And this salt is not volatile. You're not going to smell it. It's like sodium chloride. It's a salt. So one way to neutralize the scent of ammonia. Anyway, is by treating it with an acid. So the ammonia in this case gains the proton, and the HCl loses or produces an acid. And down at the bottom kind of shows you in space film model what's going on, and you form a salt here, in this case ammonium chloride. Okay. All right, now we're going to talk about, this is where I started off, strong acids and strong bases. When we talk about this, we're talking about how much of that acid dissociates. We're going to learn that a lot of these acids dissociate, not a lot, some of these acids dissociate 100%, and others not as much, okay? And all that does, or that means is that there's less protons in water, which makes it a weaker acid. And that's why you have a pH range where you have something that's very acidic like your stomach and something not as much acidic like Dr. Pepper, which has a pH of 5. We'll learn more here in a bit. Here's some examples of some strong acids. Hydrochloric acid, which we talked about at length already, and then HNO3, which is called nitric acid, and then H2SO4, which is called sulfuric acid. Notice something here, NO3 minus, that's nitrate, remember that, in polyatomic ion? If I take a proton and I put that back on to the nitrate, guess what I make? I go from nitrate to nitric acid. This is sulfuric acid. Does this look familiar? SO4 -2, the sulfate, polyatomic ion. If I put 2 protons back on here, I make sulfuric acid, okay? And then guess what? If I got the chloride ion. If I put my hydrogen back on, I make hydrochloric acid. So a lot of these acids are made from putting a proton back onto a corresponding anion. Okay, strong acids, because they break apart 100%, meaning there's more ions in solution, which makes more proton solution in solution, which makes it a lot stronger. Okay. So here's hydrochloric acid. Strong bases. Same scenario, in that when they're put in solution, like sodium hydroxide and potassium hydroxide, they totally break apart and they produce a lot of hydroxide, what makes it a strong base. We're going to learn the reason these ionic compounds are 100% strong is because their solubility in water, they're soluble in water. We're going to learn that and we have solubility rules, which is on your periodic table. We're going to learn about those. When something is soluble, they dissociate 100%. Okay. Sodium, potassium, hydroxide, soluble, 100% dissociation. We're going to find that some ionic compounds don't dissociate as much. Magnesium hydroxide, aka milk of magnesia, does not dissociate 100%, maybe 5%, maybe much less. Bulk of it's still intact. Makes it a weak base, okay? And is related to its solubility in water. All right, so this is an example of what's happening in where sodium hydroxide totally dissociates through the ions, and the same is true for hydrochloric acid. Okay, now how do we depict this in diagrams? If you look at the left diagram, that shows a strong acid where all of the ions are totally separated and dissociated. Now, I would add maybe 3 to 4 pairs and to show a strong acid. And here in this case, hydrochloric acid. And when you draw them, do make sure, see, I got 3 chlorides and 3 protons. So make sure they're paired up, okay? Also make sure that you got the ions, because remember, these are ions in solution. This is a very strong acid. Same is true for sodium hydroxide. You can add 3 or 4 pairs of ions. Say I got 3 sodiums, 3 hydroxides. Again, with the charges, again, showing totally 100% dissociated. Okay, in a beaker diagram. So here are the strong acids: hydrochloric acid, nitric acid, and sulfuric acid. Earlier I showed you the nitrate ion. You remember that? Which was a NO3 minus. If I put that proton back up, I have nitric acid. So I just remove the ATE, add the IC, and then add the word acid. Okay. Same with the sulfuric acid. This was sulfate ion, SO4 negative 2. I put my 2 hydrogens back on that. I get rid of the ATE, add ICE and acid, sulfuric acid. Okay. And over here was the chloride. Chloride, and if I put the hydrogen back on, I get rid of the IDE, okay, and put in the chloric, and the acid, and the hydro, and I got hydrochloric acid, or hydrobromic acid, so on and so forth. Strong bases were potassium hydroxide and sodium hydroxide. And again, what we mean by strong is these guys totally dissociate into the respective ions 100% or approximately close to it. Now, we have weak acids and weak bases. That means that they dissociate not 100%, but maybe 1 to 5%. And we show that by this reaction here and with the double arrow. Notice that this is acetic acid, a very general formula for acetic acid. The bulk of it's still intact. We have a double arrow, meaning it's going left and right. Well, there's not a lot of protons in there or the corresponding anions. The bulk of it is still combined, okay? Because they're not dissociating as much as the strong acids. Another example, well, that's for an acid. What we have up here are some examples. HF is called hydrofluoric acid. That's a weak acid. This one here is carbonic acid. Recognize the CO3 carbonate. 2 protons back in, carbonic acid. This is acetic acid, aka vinegar. Find that in Italian dressing quite a bit. This is also the acetate ion. Put a hydrogen back in, now you got acetic acid, right? And then we got phosphoric acid. If you drink a lot of soda pop like me, you drink a lot of that, phosphoric acid. But it's a weak acid. Notice the PO4, phosphate, -3. Add 3 hydrogens back on, now you got phosphoric acid. All right, so they don't break apart as much. This is the acetate right here, ion. And this is the proton. So that is why they are considered weak, because the dissociation is not very much. And how do we demonstrate that? Oh, a weak base. I did mention magnesium hydroxide. Here's the formula, double arrow. It is a weak acid, base. It's a base because of the hydroxide, but it's weak because its solubility is classified as insoluble, which means that the bulk of it is still intact and down in the bottom of your container is a solid. Milk of magnesia is like that. If you ever take some out and put it in a glass, you're going to see eventually, let it sit there, white material settle to the bottom. That's because the bulk of it is not soluble. Yes, there are some in solution. Some of the ions do dissociate, but we just put in one set, okay, to show how very weak. It's not as strong as the others. You gotta bear with me 1 second. And my apologies, I needed to do something real quick. Okay, so how do we show these graphically as far as weak bases and weak acids? Well, if you look at the beaker on the left side, the HF, which we define as being a weak acid, they're shown still combined. Okay, and then we just do one set of at least one set of ions to show that the majority of this HF, hydrofluoric acid, is still intact. So there's less ions in solution, less protons in solution, and therefore weak. Okay, the magnesium hydroxide, we're going to see that solid here. It is insoluble in water. Is defined as insoluble, but even though it's defined as insoluble, there's always a very small amount still in solution. So the bulk of it is shown down here at the bottom with the formula, and that's supposed to show that it's still solid down at the bottom of the container. But then we show a little, at least one set of ions. And of course, we got two hydroxides because it's parentheses, we got two hydroxides with one magnesium ion, okay? So that's how we depict a weak acid and a weak base in a beaker, of water, if you will, a diagram. Okay, so some of the weak acid we showed is hydrofluoric acid. I think I mentioned this to you. If you stain glass, this is probably what you're using, HF, hydrofluoric acid. Used a lot to stain glass. And then we got carbonic acid, phosphoric acid, and acetic acid, okay? And if you think about this, we have the carbonate ion. This is carbonate from the polyatomic ion table. This is PO4 negative 3 phosphate. And then we have the C2H3O2 negative, which is called the acetate, also in your polyatomic table. When we put the corresponding protons back up, we get rid of the 8, add the ICE acid, okay? Oh, and of course, we got the chloride. Now, in your nomenclature exam, it doesn't distinguish, and be careful. All the halogens, like binary acids, like HF, HCl, if it is a aqueous solution, so this is hydrochloric acid, for example, if it is an aqueous solution. If it's not, and it's just hydrogen chloride, okay? And when you're answering the nomenclature exam, think aqueous, okay? Think aqueous. But I go in there and I give credit for either one. Okay. And the weak base is just one of them, but there's a multiple one. And all defined by the solubility rules. So magnesium hydroxide. And again, what weak means just means that they do not dissociate as much as a strong acid or strong base. There's most of it still intact. And so if we look at these diagrams, you may be asked, well, which one's a strong acid? Well, by definition, an acid is anything that produces protons. So we're going to be looking for H pluses. And we can see that both all three, A, B, and C, have H pluses or protons. However, if you look at A, they're all dissociated. No one is combined. And so A would be designated as the strong acid, whereas the weak acid would be B and C. Okay, you can see that the majority, there's a lot of HA still combined in both cases. And if I needed to compare just these two and see which one's stronger relative to B and C only, then I would have to say B was, simply because there are more protons in solution for B than there are for C. So within B and C, B will be a little bit stronger. And the question then asks, well, which one is a strong base? Well, there's really nothing here, especially because normally we're just simply talking about hydroxide, okay? Hydroxides, and there's no hydroxide in solution, so we don't have any base to deal with. And here's the pH scale I mentioned to you. And you might be familiar with this. If you have a fish tank, or if you've got a swimming pool at home, I'm sure you go out there with a little testing kit to figure out what the pH is of your fish tank or swimming pool, okay? So the scale runs from 0 to 14. Neutral is 7, okay? Anything less than 7 is considered acidic. Acidic, less than 7. And anything greater than 7 is considered basic, or alkaline is another term you may hear, okay? Alkaline. I'm going to introduce you to something new here, where we have the brackets around the proton and the brackets around the hydroxide, okay? That is simply called concentration. It's a specific concentration called molarity, and I'll introduce that right here. Okay, it's called molarity, and it has units, and we're going to get into these units much further down the road, but those units are moles per liter, okay? Moles per liter. So for right now, just think concentration. Now, when the concentration of the proton is greater than the concentration of the hydroxide, in this scenario, you're acidic, okay? When the concentrations are both the same or equal, they basically neutralize each other, you're neutral, or 7, neutral conditions. And then if your concentration of your hydroxide gets greater than the proton, then you're in the basic range, okay? Basic range. Now this strongly acidic can vary a little bit. It could, strongly acidic could be, it depends on the scale, but it can be as much as 2. The same is true for basic. It can be, about 12 to 14. Okay, but you can notice there's a range here in between of acidity. All right, and that is basically what I just stated to you earlier about the concentration being acidic or basic and neutral when they're both the same. Okay, now pH is nothing more than a mathematical calculation. That's it. There's nothing special about it. All you need to know is the concentration of your proton concentration, your acid concentration. So if you take the log of that concentration, you end up with a negative number, okay? And it is defined as the pH is equal to the negative log of your proton concentration. So remember this, if I were to say, I want to take the pH equal to the log, and my concentration was 10 to the negative 1, okay? Well, that becomes negative 1. The log of 10 to the negative 1 is negative 1. And negative 1 times negative 1 is a positive 1. So pH will always be, at least in Chem 130, be a positive number, okay? If you want to revert back to the concentration, you can take that pH and put a negative in front of it, and just take 10 to whatever pH power it is, and that gives you the concentration. All right. So let's do some examples. So the pH of 1 times 10 to the negative 5th is simply 5. So notice that the concentration of my acid got smaller, 10 to the negative 5th, compared to up here, and my pH goes up. So the acidity concentration goes down while the pH value goes up, okay? 10 to the negative 8, it's inferred here as 1 times 10 to the negative 8. That's simply the pH is 8. Again, look how much the concentration has decreased. 10 to the negative 8, okay? Compared to the first one, 10 to the negative 1. So 10 to the negative 3rd would simply be pH of 3. So again, we've got more concentrated, pH drops. And then which either you put in scientific notation or you put in decimal form, makes no difference. 0.001, type that in, hit the log button, guess what? You get a negative 3, and that times the negative is positive 3, okay? Now here we get numbers that are nice whole numbers, coefficients, and that's fine, but sometimes you have an uneven number, so you really would you need to use the log button, unless it's in scientific notation like this, and it's 1 times 10 to whatever, then you know the exponent will be the pH. So this guy would be a pH of 8, because taking that decimal and writing in scientific notation gives you 1 times 10 to the negative 8, which is a pH. And the log of that is 8, okay? Some idea, some examples of pH and normal things that we have. Vomit are roughly 2. Well, that varies, but of course it's going to be 2 because your stomach is, hydrochloric acid somewhere in that 1.5 range. And yes, it burns going up because your esophagus cells are not made to protect the tissue like your stomach, inside stomach cells are, okay? Lemon juice, about 2.5. Coffee, that varies really with the coffee you're doing. That's about 5. Saliva, again, depends on what you're drinking and eating. Blood is pretty much set, about 7.4, a little bit of variation, but it's a very important pH. Just slightly above pH 7 or neutral. Milk of magnesia, it's alkaline, 10.5. That's why you drink it when you have, acid reflux, because that's going to neutralize the acid in your stomach. Ammonia, 11.7, and a lot of colas range from about 2.5 to about 4-ish. And root beer, which I was surprised when I first saw this number, was a lot more, not as acidic. And, a question that I drink a lot of soda pop, a lot of diet pop, and I get yelled at, "You're drinking too much soda pop. It's too acidic." Bear in mind, soda pop's 2 to 3. You're dumping it into a stomach that has a pH of 1. Are you really affecting your pH? It's my response, Besides, I like my Diet Coke. All right, buffers. Buffers, straightforward, nothing big to say about this other to say that all they do is maintain the pH at whatever pH value you need, okay? So, for example, your blood has to maintain 7.5, 7.4-ish. You have a buffer system in your body, and all that means is if a base, external base comes in, then the acid part of that buffer reacts with it to maintain that pH, or if an acid comes in, then the base part reacts with it to keep with that pH, okay? Keep the pH constant. Now, with respect to this reaction, we have a HNO3, which they're asking here, who is the Arrhenius acid? So remember, anything that produces a proton, which would be nitric acid, right? Because it's producing a proton here. And the Arrhenius base would be anything that produces the hydroxide. So that would be calcium hydroxide, acid-base reaction, okay, with nitric acid and calcium hydroxide. So it's a neutralization reaction because that acid and that base gets neutralized to form water, okay? And specifically 2 waters because I got 2 protons and 2 hydroxides. And those are going to make 2 waters. And we're going to learn more about that. We call that stoichiometry, that ratio. Okay, we know that calcium is bonded to 2 nitrates. Why? Because calcium is a +2. The nitrates each have a -1, so it has to be 2 nitrates, and we put parentheses around it. You may be asked questions like this: draw pictures, diagrams of the following. Okay, well, how do I answer this? Well, the first step is this. You first have to define whether it's strong or weak, okay? All right, so we know that by definition that this is a strong acid, okay? This is a weak, this is a strong base, and magnesium is a weak base, okay? So once we know that, we know how many ions to put in our drawings. Either we're gonna put some that still be maintained together, or all of them are gonna be dissociated. Okay, so we have to answer the strength. Now, right now, we told you that magnesium hydroxide is a weak base by definition, but we're going to learn to use the table, the solubility table, to get a better grasp as to why magnesium hydroxide is weak and why potassium hydroxide is strong, and it's related to their solubility. All right, so we just defined that magnesium nitric acid is strong, so we're going to throw in at least 3 or 4 pairs of ions, totally separated, okay? HF is a liquid, and the way we draw it is we maybe show at least 1 set of ions. The rest of them, 3 or 4 ions or HF molecules are still intact. Okay, so you can see there's less charges in solution compared to nitric acid, right? Because it's a weak acid. Potassium hydroxide, a strong base. So we draw 3 or 4 pairs of the potassium and hydroxide, and they're totally separated. Weak magnesium hydroxide is drawn, like we showed earlier, okay, with the bulk of it down at the bottom of this container as a solid. That's supposed to depict a solid, and at least 1 set of ions in solution. Notice we have 2 hydroxides, right? Because we have 2 hydroxides in the formula. Okay. And there's the solubility rules that we're going to talk about. So let me summarize this. So Arrhenius acids they make protons when we put them in solution, okay? They dissociate. Where Arrhenius bases produce the hydroxide ion solution. Okay? So Arrhenius acids are really covalent. Arrhenius bases are really ionic. With respect to Bromide acids, similar to the Arrhenius acids, you're going to lose or produce a proton. A proton is being generated someplace in solution. Where they differ is the definition of a base. A base has not, for a Brownstein Lauer, has nothing to do with hydroxide. It can. It means hydroxide does fit into the definition, but it also allows other compounds that don't deal with the hydroxide, to be called a base, and they simply just gain that proton. They neutralize that proton. Strong acids, they totally ionize or dissociate 100%, or approximately, whereas weak ones do not. Much less, 1 to 5%. Okay. The bases, same as strong acids, dissociate 100%. Ionize, dissociate, we use that term interchangeably, okay? And the weak bases, much less, like the weak acids, okay? And buffers, all they do is keep the pH constant. That's it. Okay? So that kind of summarizes your acid and base part. There's some more pH values for a variety of different soda pops. You can see tap water up high, a little bit over 7, but that varies. It depends on your water, and it varies from country to country, or city to city, I should say, and country to country. Anyway, RC Cola, which used to be my favorite, it's most acidic stuff there. All right, so why is a problem? Here you go. For your dental hygiene students out there, this can happen. You know, really mess up your enamel on your teeth due to the acidity. Which brings us to solubility. Okay, I'm trying to knock this out. I may go a little bit over time, but bear with me, okay? I only got a few more slides. Solubility deals with compounds dissolved in water, but at a specific temperature, because we know that if something is not soluble or kind of weakly soluble, we can increase it by heating it up, right? So solubility is a function of temperature. So to keep it meaningful, so to speak, we are dealing with 25 degrees temperature, okay? 25 degrees temperature, and we're dealing with water, aqueous system. So if something is classified as soluble, that means it completely dissociates into the respective ions, and we designate that by the symbol, the physical state of parentheses AQ, meaning it's an aqueous system. If something is defined as insoluble, then we give it the designation of parentheses lowercase s, meaning solid. Now, it doesn't mean that it is totally insoluble. It means there's a little bit in solution, just like the magnesium hydroxide example. We show at least one set of ions in solution. Okay, so here's the tables, and this is how it works as far as reading the table. We got 2 columns here, okay? The first column is the soluble column, right here. So number 1, I call these the big 4 here. Big 4 cations. Any anion, I repeat, any anion, whatever it may be, if it is partnered up with those big 4 right there, it is always soluble. Okay? No matter what the corresponding anion is, if it's hooked up with lithium, sodium, potassium, and ammonium, soluble. 100% dissociated, okay? Number 2, here's the acetate ion. Any cation that is bonded to the acetate ion is soluble. Copper acetate, obviously the big 4. Mercury acetate, anything I'm pulling off the periodic table, any of the metals, soluble, okay? Number 3, the nitrate ion. Any cation, just like number 2 acetate ion, bonded with the nitrate ion, it is soluble, 100%. So like the acetate, copper, acetate, nitrate, soluble, lead nitrate, soluble, etc., okay? So the moment you see acetate or nitrate, regardless of what the plus part is, it is soluble. With respect to the halides, and it's meaning the chloride, the bromide, and the iodide. As the case with number 2 and 3, any cation bonded to those is soluble except 3 of them. If they're bonded to silver, mercury, or lead, they're insoluble, okay? That means all the other metals is bonded to, soluble, except those heavy metals. Same is true for number 5, sulfate. Bonded to any metal, it is soluble except if they're bonded to calcium, strontium, barium, silver, and lead. So there's 1, 2, 3, 4, 5 sulfates that are insoluble, and all the other sulfates are soluble. Okay. All right, let's go look at the insoluble column, meaning again that they're designated with the letter S, but there's a little bit of it in solution, but the bulk of it is not soluble. All right, so number 1, which is the carbonate ion. Anything bonded to the carbonate, regardless of what it is insoluble, except, guess what? The big 4. So there's only 4 examples of carbonate that are soluble. Everybody else is insoluble. Copper carbonate, insoluble. Lead carbonate, insoluble. Sodium carbonate, soluble. Lithium carbonate, soluble. Okay. The chromate ion, just like the carbonate, everything is bonded to is insoluble unless it's bonded to the big 4. Okay. And only those 4 are soluble. The phosphate, all phosphates are insoluble, except who? The big 4. Lithium, sodium, potassium, and ammonia are the only ones, phosphates that are soluble. Everybody else is insoluble. Sulfides are also insoluble, except, sound ditto, the big 4, but not only the big 4, but 3 more. Calcium sulfide, strontium sulfide, barium sulfide. There are 7 examples of sulfide compounds that are soluble, and everything else, regardless of what it is defined as insoluble. Then the hydroxides, and we got ditto again, insoluble except the big 4 and bonded to calcium, barium, and strontium. So again, there's 7 examples of hydroxide compounds that are soluble, and anything else that is given to you or you're seeing makes it insoluble. Okay, so that's essentially how this table works. And so let's look at some examples. Let's clear this up a little bit. Okay, first one says Na, and once you see sodium, you don't have to go any further. You see sodium, you're number 1 here. Sodium, all the time soluble. And guess what? There's potassium. That's true for over here. So those 2 guys are always going to be soluble, no matter what follows after the potassium and the sodium. And so sodium sulfide is soluble, hence we put aqueous. Okay. Hydroxide, aluminum hydroxide. Okay. So we go to the hydroxides. It's number 5 right here. It is in the insoluble column, so it is insoluble, but let's verify it. Unless it's bonded, like we said, to the big 4 or calcium, barium, or strontium, of which aluminum is not. So therefore, aluminum hydroxide is insoluble. But there's, again, a little bit in solution. Silver bromide. Okay, well, we could look for the bromides. Bromide's a halogen right here. Normally they're soluble unless it's bonded to silver. So in this case, silver bromide is insoluble. All right, now we got the next one, calcium carbonate. Okay, we go to the carbonate, which is right here. Normally, carbonates are insoluble unless they're bonded to the big four, of which calcium is not. So therefore, calcium carbonate is insoluble. You also find that ring around the tub, that stuff, this material on your tub, and it hasn't been cleaned out in a while, or around the spigot or the handles. That's a lot of calcium carbonate. And then the last one, because you salt potassium, automatically you don't have to go any further. Whatever's bonded to potassium makes no difference because it's always soluble. Okay, so that's essentially how we utilize the solubility rules to determine solubility. Okay, because when we deal with solubility in these compounds, we deal with electrolytes, because remember, electrolytes are nothing more than atoms that have either gained or lost electrons. So that is what you're drinking. When you drink your electrolyte drinks, you're drinking atoms that are either cations or anions. And why would you drink that? Because you need electrolytes in your body. Without them, they do not conduct electricity. We cannot move signals from point A to point B. So strong electrolytes are good conductors of electricity. They completely dissociate or ionize in water. So anything that's defined as soluble, any ionic compound defined as soluble is strong. Any of the strong acids, any of the strong bases, okay, anything that's soluble or strong, base or acid or base, are strong electrolytes because they dissociate 100%. And there's some examples of them, okay? Non-electrolytes, these are covalent compounds except acids, okay? Acids are covalent compounds, but because of the nature of the beast, they dissociate. But other than that, covalent compounds do not break up in solution in water, and so therefore do not form ions, and therefore do not conduct electricity. So if I had pure 100% water and I put sugar in there, sugar is a covalent compound, it will not conduct electricity because there's no charges on there. Or if I put any other covalent compound. A weak electrolyte are poor conductors of electricity. It will conduct electricity, but that's not a lot because there's not so many ions in solution. So all your weak acids, all your weak bases, and anything that's been defined as insoluble as far as an ionic compound, those guys are weak electrolytes. So there's some examples there. HF was a weak acid, magnesium hydroxide, etc. Okay, so this summarizes strong electrolyte, weak electrolyte versus non-electrolyte. Okay, this is just kind of demonstrate what these electrolytes or these ions are doing in solution. So we got a beaker here with some current running through. Those ions, because they're there, their charge makes a conducting solution. And therefore you have a low charge up there, shows that you completed the circuit. Those ions act as the light switch, as they close the circuit to have the electricity run through that circuit, okay? If those are not ions and they're covalent compounds, they will not conduct electricity because there's no charge for them. Electricity is not conducted, okay? And we depict things as follows. So here they're asking which is strong, which is weak, which is not. We can see here, we can answer the non very quickly here because we have this species here, carbon and hydrogen. That's it, nothing else. There's no metal in there. It's not an acid. Remember, as a general guideline, H should be written first, followed by whatever is going to follow that. And that represents an acid. H after the centratom, not a good chance it's not an acid. So this is a covalent compound. And there's no charges. So that is a non-electrolyte, non-conductor. We talked about magnesium hydroxide at length, how the bulk of it is down at the bottom because it is a weak electrolyte. So magnesium hydroxide will be a weak electrolyte simply because the majority of the material is insoluble. Okay, so this would be classified as a solid here. Potassium chloride, extremely soluble. We got potassium out front, part of the big four. So all the ions are in solution and separated. So we end up with a strong electrolyte there, okay, because of all the ions in solution. What we got here is a listing of things, and we go through each one. Well, first one, we got to name it so we know what we're looking for, right? So the first one is barium sulfide. Okay, so you're asking sulfide. Okay, I can go to the solubility rules and look up for the sulfide. And you will find that normally the sulfide is insoluble, okay, which will make it a weak electrolyte, except when it's bonded to barium. And when it's bonded to barium, it is soluble. Therefore, it is a strong electrolyte. Okay. We got silver chloride here. And anytime you see silver, unless it's not bonded to nitrate or acetate, it's a good chance it's insoluble. It's a heavy metal. And so we go verify it. We look at the chloride under the solubility rules, first column. Chlorides are soluble except when they're bonded to silver, which makes it insoluble. Therefore, it's a weak electrolyte. Potassium nitrate, don't have to go any further. You got potassium way up front, okay? Makes it very soluble, makes it a strong electrolyte. H2, H you got up front, that's an acid, that indicates an acid, okay? So you go through your list of the acids, and this one happens to be carbonic acid, excuse me. And it is classified as a weak acid, therefore a weak electrolyte. Carbon dioxide, nothing but covalent bonds here, okay? No metal, no acid, so it's a covalent compound, so that means it's a non-electrolyte. Number 6, boom, sodium. If I'm going any further, it's a strong base. Why? Because it's very soluble. Okay, anything bonded to sodium is very soluble, and the reason it's a strong base because it produces hydroxide ion. That's why it's a strong base, strong electrolyte. Calcium carbonate, we did talk about this. The carbonate normally is, the calcium carbonate is insoluble, making it a weak electrolyte. Number 8, you may not know what it is. That's okay, but you can analyze it and see, I got nothing but carbon, hydrogen, and oxygen. Nothing else, no salt, nothing else. It's basically all covalent. If it's all covalent, then it's a non-electrolyte. And number 9, again, here we go again with sodium. That's all she wrote. Don't have to go any further. Doesn't care what's afterwards because you know the big 4, always soluble, which makes it a strong electrolyte because it's soluble, 100%. And then lead, that's a good indication that lead is insoluble, you know, heavy metal. We will verify it. The sulfates with lead is classified as insoluble, therefore making it a weak electrolyte, okay? Weak electrolyte. And so the point about this is if it's to classify it strong, it has to be either a strong acid or a strong base or soluble if it's an ionic compound, okay? If it's weak, it's going to be a weak acid, a weak base, or classified as insoluble as an ionic compound. And if it's all covalent bonded, there's no ions in solution, is simply an non-electrolyte. Okay, will not conduct electricity. Okay, and that, ladies and gentlemen, I went 4 minutes over, sorry, is the end of chapter 4. Any questions? My apologies for starting in the wrong chapter. Wrote it backwards. So we're done with 8, we're done with 9. come next Friday, we will start with chapter 10. Okay. And also we have next week the exam. So don't keep up with your homework. You have any questions? We're free if you need tutoring. Remember, we got tutoring. Also, remember I sent an email about 2 professors at GCC were having sessions, 2 work sessions. I asked them, you guys, even though you're SCC, they have no problems of you guys going there and going in with questions, an additional aid for you. Okay. All right. So